maybe another force does negative work. That means that that particular force makes a withdrawal. It takes away from the motion energy. So the work being plus 0 or minus is the same plus 0 or minus that you have on your bank account. If you look at your bank statement, right, you have deposits and withdrawals. Okay, there's no $5 to the left. Okay, it means that someone took out $5, right? And positive $5 doesn't mean $5 to the right. It has nothing to do with the direction. It has to do with putting money in. Okay, so that's what we have. And what you're doing when you calculate the net work, you're balancing your checkbook. You're looking at all the different forces. Some are going to add energy, some are going to subtract energy maybe, some are going to not touch the balance. Okay? So this is looking at all your transactions. Now you don't need vector addition to balance your checkbook, right? You just look at what goes in and what comes out. So some works may be positive, some works may be negative, some may be 0. And what you're trying to do is figure out, at the end of the day, do the deposits outweigh the withdrawals or vice versa? So when the net work comes out positive, 0 or negative, that tells you overall how your balance has changed. Okay? It tells us you have the overall amount of kinetic energy has increased, decreased, or stayed the same. Okay? So if the deposits, the positive works add up to the negative works, the withdrawals, you're of course going to have no change overall. Does that make sense? So that's what we have here. We're thinking of every force that acts on the object in a very different way. We're thinking of every force that acts on the object. Is it either going to add to the motion energy, is it going to take away from the motion energy, or is it going to have no effect on the motion energy? Okay? We're thinking of it all in terms of transactions to this pool of the object's motion energy, the kinetic energy. Have any questions on that? Yeah.
Why did you assume when you tried the work in theorem, initial velocity is 0?
Well, because otherwise I couldn't say this is 0. So it's not really necessary for you to start at rest, but I'm just kind of making assumptions that allow me to do this with the math we have available.
If angle is 0, then it's 0, isn't it?
I'm sorry?
Oh, if angle is 0, theta is 0.
Cosine of 0 is 1, not 0.
Oh.
Any other questions? Okay, so that is kind of where we're going. We're going to kind of ditch vector land and try to be in scalar land as much as possible. So let me write down a force problem-solving strategy, a work problem-solving strategy, and then we'll take it out for a spin. So this is the work problem-solving strategy. Here's how it's going to go. First, you of course need to identify your object of interest. And then identify the forces that act on it. So basically cleaving the object apart from the rest of it, which is the environment. Now those two steps are, of course, the exact same first two steps of the force problem-solving strategy. You need to pick one object to focus on and see how the outside environment affects it. But the next step, we're going to take a complete left turn and go in a different direction. Instead of hunkering down, building our scaffolding, setting our axes, and being ready to do SOHCAHTOA with all that stuff, we're not going to do any of that. Okay? So the next step is you're going to compute the work done by each force. You're going to do that with that equation we developed. This one. So this is meant to be a very, very straightforward formula to use. You just put in the sizes of these two things here. So those are always inherently positive. You never have to worry if it's cosine or sine, because in this equation it's always cosine. But depending on the angle, the cosine could come out plus 0 or minus. And that's going to be whether the force is more with you, guiding you only, or more against you. And that's going to then control whether the work is positive, 0, or negative. Which is to say, does it add kinetic energy to the object? Does it have no effect on it? Or does it remove kinetic energy? Notice that there is no SOHCAHTOA necessary here. You don't even need to set any axes. The only thing you need to do is identify what angle each force makes with the displacement. Okay? So there are no axes or components necessary here. So all of the kind of scaffolding that you have to put on those problems, or hopefully you're at that point where you realize you got to be really careful about your pluses and minuses, what's in the plus x, plus y, minus y. Got to be really careful with that, so sines and cosines, none of that stuff. So then what do you do with that? Well, once you've figured out each individual transaction, then you balance your checkbook. And this is a really easy thing to do because it's a scalar sum. Okay? It's a list of numbers. So it's a scalar addition. It's a string of numbers. Yes, some might be plus and some might be minus, but it's still a string of numbers. Right? There's no SOHCAHTOA necessary to do a scalar addition. It's not vector addition. And then, once you have that, if there is anything left over after all your additions and deposits, with withdrawals and things like that, that is your overall, whether or not your balance went up or down. So that will inform how much kinetic energy is changed overall. Remember, that's 1/2 mv final squared minus 1/2 mv initial squared. And at this point, you will have one monster equation, which you can solve for something involved. So then you just solve. Okay, I guess I can put step 5, solve for something. Solve for something. It could be anything really involved. Could be the final speed. That's what's going to be in my examples that I'm going to do momentarily. It could be, I don't know, the mass. It could be one of the angles that one of the forces make. It doesn't really matter. You've got this big equation. Any one thing could be left out. Okay? So just be systematic in writing it down, and don't be obsessed with whatever one thing they seem to be asking for. So there's one piece of advice I could give you on physics in general, is to be patient, set up the problem, and then at the end, trust that you'll have enough to solve for the one particular thing that they ask for. Some problems will give you A and ask for B. The next problem will give you B and ask for A. It's good to not be too obsessed with the particulars of what they're asking. Okay? So just set up the problem with the givens, and then crunch it through, and then at some point it'll just become a matter of algebra for isolating whatever particular thing they left out. Okay? Okay, so let's take it out for a spin, see how it goes. So this is going to be a problem that you certainly can do with the forces method. This is a problem you should be able to do for the first exam. So if I asked you to do the problem like this for Thursday, you can do it. I just want to do it in a different way. I'll talk through how to do it with forces first, but then I'll do it with the new method, of course. Here's my problem. I have a horizontal surface with a mass on it. That mass is 10 kg, and it's initially at rest. The it's going to experience a pulling force of magnitude 50 newtons. It's going to be horizontal like this. And there is friction. And just to save myself a step, for instance, on homework number 5, you learned how to check if this pulling force is enough to move it. Okay, so of course you double check, does the pulling force exceed static friction max, right? Let me not do all that rigmarole here, so I'm going to just assume that this pulling force is greater than the static frictional force max. So it's going to move, okay? And let me say that once you move, of course, you need to still factor in kinetic friction. Let me give you the static frictional coefficient, or the kinetic friction coefficient, 0.3 is that value. Okay, so that should be enough information to pose my question, which is, after it slid 5 meters, what is the final speed? Okay. So I'm going to exert this force. It's going to start this thing from rest. It's going to make it slide. It's going to go faster and faster, and after 5 meters, how fast is it going? So let's do the first 2 steps. Those first 2 steps are the problem-solving strategy are common to both the work method and the forces method. So object of interest, pretty obvious. It's that box, whatever it is. Forces that act on it, one of them is given, but I do have several others. Force of gravity, of course, pulls down. Normal force perpendicularly away from the surface is up in this case. And then kinetic friction acts against the motion. So I have a total of 4 forces to consider. So at this stage, let me just take a break, not continue with the work method, but just talk through how would you do this if I asked you this question on Thursday. What steps would you take? Well, here's what I recommend, right? So step 3 in the problem, the force strategy is pick an axis. Pick an axis to either minimize your SOHCAHTOA, or because you know which direction the acceleration is in here, no brainer, you can actually have both of those considerations be in place. If you pick axis something like this, the acceleration will be all x, no y, and all of our forces are along those axes already, so no components necessary, right? So by making sure f net y was equal to 0, ... we get this, of course. Hopefully this is not news at this stage. And then f net x would be the pulling force minus whatever friction could take off, right? You should still have some forward net force left, because of course if that pulling force was enough to overcome static friction, kinetic friction is even weaker. So there will be some net force going forward. This is mu k times n we just discovered from the y direction was mg. And whatever imbalance there is in those x forces will lead to acceleration. Now the acceleration, of course, still is not what we want. Acceleration is just a means into the kinematics. So we'd use that in one of our constant acceleration equations, and we could get the final speed after sliding 5 meters. Okay. So you're, of course, what's the minimum number of variables you need to solve one of those equations? 3. So what are they? Initial speed, 0. Displacement, 5 meters. And of course, I just would have solved for the acceleration, so that's 3. And so I can solve for v final. Don't know, don't care about time. Use equation number 3. Okay. So that's your classic force structure. I know I went through that kind of quickly, but I know that's mostly, I hope that's mostly old news. But I want to now show you with the work method. Before I do that, are there any questions? Okay, so let's do the work method. I don't actually need axes at all, but one thing I am going to do is I'm going to put in another important vector here, the displacement. I'm doing that in different colors so you don't confuse it. It's not a fifth force, right? There's 4 forces, but it's another vector that I need in this case. And then let me just make a little graph here, or a little table. For each force, I'm going to tally what is the angle that that force makes with that displacement vector. And using that, I'll compute the work. Let's start with the force of gravity. What is the angle the force of gravity makes with the displacement? 90. What is the work done? 0. So in this problem, the force of gravity acts perpendicularly to the motion. Never helps you, never hurts you. You're moving horizontally. Gravity has no effect there. So gravity will not neither add to nor subtract from your motion energy. Okay? Let's do the normal force. What is the angle that that makes with the displacement? 90. So how much work does that do? 0. So out of the 4 forces we have that act on the object, 2 of them do not have any effect on the motion energy. They neither add to it nor take away from it. I'm not saying the forces are 0. Obviously, the forces are there, but they play a guiding role. They don't affect how fast or how slow it's going. Let's do the pulling force. What is the angle the pulling force makes with the displacement? 0. So the force is definitely more with the displacement. In fact, this is as with it as it can be. They're in the exact same direction. And so we will get a positive work. A positive work which will add to the motion energy. So how much is it? Size of the force, size of the displacement, cosine of 0. Cosine of 0 is +1. Otherwise, I just go ahead and I put in the numbers. Those 2 other numbers are given, right? The size of the force is 50 newtons, and the size of the displacement is 5 meters. So 50 times 5, it's 250. And the units are joules. So we find that if this object has a store of kinetic energy, by the way, we should mention, what's the initial value of the kinetic energy? How much motion energy does it have to start? None. Its initial speed is 0, right? So we are starting with an empty bank account. Okay? There's nothing in it to start with. And then one of our forces, being that it does positive work, makes a deposit of 250 joules into it. So 250 joules goes in, but that is, of course, not the end of the story, because we do have another force. The final force is kinetic friction. And what is the angle that that force makes with the displacement? 180. It acts exactly against your motion. That's what friction always does. It always opposes you. So, if we calculate that, we have the size of the force, size of the displacement, cosine of 180. And cosine of 180 is -1. So we are going to get a negative value for work. All right? Well, here's one issue, is that the size of the frictional force was not handed to us on a silver platter. So we're going to have to borrow a little cup of sugar from the forces method This is why we have to do this second, because occasionally we do need to refer to certain things. For instance, we know that the frictional force, its size is mu k times n. That's no big deal, that's just an equation. But now that we've just gone next door to borrow a cup of sugar from the forces method, we're going to have to go back, borrow a few eggs, because there is no way to figure out what the normal force is besides looking at the forces. So we have to rely on this fact to get this and substitute in n equals mg. Okay? So it's not quite as clean of a split between these two methods. In fact, you might question, if we have to borrow that much from forces, is this thing really worth it at all? Well, we'll see. Okay? The jury is out right now, for sure. Okay? If we have to borrow this much stuff from the forces method, it's not worth it. But we're not done developing it yet either. There's more to come. I just don't want to have to develop the entire method right now without, because that would be like 2 or 3 lectures worth of abstract stuff. So I'm taking a break and doing some example problems. So if you do this, you'll get minus 147. So the work done by the frictional force is minus 147. That means that this particular force is going to remove 147 joules. I should point out that the object started off with 0 joules, so there wasn't 147 joules to remove in the first place. There's 147 joules to remove because another one put in 250. You can kind of think of friction like the tax man, okay? If you have no money, you owe no taxes, right? But if you get money coming in, some fraction of it will go out in taxes, okay? So we have 250 joules going in from one force, but 147 going out due to another. We still have more money than we started with and more kinetic energy, but not as much as if it were the pulling force were there alone, right? So we go now to the next step, step 4, and we just balance our checkbook. The net work, well, we had 2 forces that had no effect at all on our kinetic energy balance. We had 2 forces that did, and we get overall the net work was a positive 103. So overall we have 103 joules more of kinetic energy at the end than what we started with. So now we know that the difference between the final and initial kinetic energies is 103. We have 103 more than whatever we started with. What do we start with again? None. So apparently, the final kinetic energy is, of course, 103. If you have $0, someone gives you $103 overall, you have $103 now. And then, of course, if this is how much motion energy you have, you can calculate how fast you must be going. And you can calculate and find that the speed is 4.5 meters per second. You can try it with the forces method, make sure you get the same thing. Of course, these are just 2 different ways to do the same problem, so the answer has to be the same regardless. That's kind of a flavor of how it goes. And obviously I didn't do this symbolically, which I generally prefer, because I wanted to talk about these as real tangible numbers. What does it mean when a number is positive or negative? It means when works are positive or negative, they're transactions on the kinetic energy balance. Okay, are there any questions on that?
Sorry, just
Yeah.
that last step where your final kinetic energy, this 103 joules, how did you plug that into the equation right below?
How did this go into this?
Yes.
That's the definition of kinetic energy is 1/2 mv squared.
Okay.
Right? Is that what you mean?
I'm just, yeah, I don't know how you calculated VF at that?
I saw 1/2 mv final squared is 103. I know m was given.
Okay.
So I just solved for
So
the
you said
v.
equal to-
Yeah. Any other questions? Okay, so let's try another one, kind of similar. I'm not going to do the whole thing in terms of numbers, but just want to give you a sense of certain things. So this is an example, sort of. Just want to sketch it out. So let's do the same thing basically as the last problem, but on an incline. All right. So one of the nice things about an incline is that in order to get something happening, right, get some motion started, you don't need a special pulling force. A component of gravity may do that for you, right? So let's say we attacked this problem similarly. We put an object that rests on an incline